Today's lesson is the electric field and the electric force between two charges. Well, first, if we take some charge, we can call Q1. This is some charge Q1. And then we take another charge, Q2. And this Q1 and Q2 can be different from each other, or they can be equal to each other. So for simplicity, we take this charge to be positive, and this one also to be positive. So we have two positive charges. And we also have a distance between them, which we can call R. So the force between these two charges will be an electrical force, which we call F. And this F depends on Q1, Q2, and also on the distance between them. So if Q1 is large, F will be large. If Q2 is large, F will be large. If R is large, F actually will be small. So this F is equal to some constant K times Q1 times Q2 divided by R squared. Now we know these three parts here that we have, Q1, Q2, and R. There you can see them, they're in the picture. But this K here we don't know yet. K is a constant, okay? And this constant actually is equal to 1 over 4 pi epsilon 0. So the main constant, actually the constant of nature here, is this epsilon 0. This epsilon 0 is a universal constant called the permittivity of free space, and it's equal to 8.85 times 10 to minus 12 Coulomb square over Newton and then meter square. So physicists, they don't want to write 1 over 4 pi epsilon 0 all the time, because they always have to write the force, the electric force, and the electric field, and this K always shows up, this 1 over 4 pi epsilon 0. So they say we might as well replace it with K instead of keeping writing all the time this. So now this force that between the two charges is equal, is the force that's acting on Q2 is equal to the force that's acting on Q1, even if Q1 is different than Q2. It's like if you have, for example, two football players, one football player that's big, the other one is small, and then they push each other. Let's say they're standing on ice and they push each other. Of course, the smaller will go far away compared to the bigger one, but the force that will act on both of them is the same, even though one is bigger than the other. So in this situation, even though Q1 is different from Q2, the force acting on Q2 by Q1 is the same as the force acting by Q1 on Q2. So since these charges are positive, the force will be pointing out, okay? And we can call it F. Here also the force is pointing out. So now if we need to see how the electric field look here. Now if we take the positive charge Q1, let's take this positive charge Q1, okay, it's positive. The electric field will actually look like this, will be coming out of the charge like that, symmetrically, coming out radially like that. And if we take another charge, for example Q3, and this charge is negative, this one is positive, this one is negative, the electric field will be going into the charge. So these two charges, their field are different from each other. One, the electric field go into the charge, the other one goes out from the charge. Now these two fields interact with each other. You can picture these fields as, for example, you can picture them as they have hands or tentacles, and those hands, they interact with each other, so there'll be a force between the two the two charges or the two things that have these hands. They're pushing each other or can be pulling each other in. So these fields, they're kind of like extension of the charge that interact with another charge and with it or with its extensions. So the field will be coming out of Q1 and going to Q3. And you can see this one coming out, going like that to Q3, and here this one like that. So you have this field between the two charges. The field between the two charges. So these two charges, you can see that these hands or these tentacles or these extensions, they're interacting or touching and kind of like pulling the charges inward. So if these Q1 and Q3 were really free in space, they will move towards each other. Okay? But let's now take the case when the charges have the same electric field or the same sign, which means Q1 is positive and Q2 is also positive. So both charges are positive. So this Q1 will release a field coming out like that, and this Q2 will also release a field, or a field comes out of it like that. Now these charges, they will actually repel. They have the same sign. They will push each other out. So the field will not try to join, will try to repel from each other. So these fields, it's like they don't like each other. So they can move out like from the other field. So this one will move out like this. This one also will go like this, move away. So these charges are these fields are moving away from the field of the other charges. So let's see if these charges have the same magnitude. Let's see, for example, if Q1 is equal to Q2, okay? Therefore, the field, the electric field here at the center between them will be actually 0. So you won't have any electric field at the center here, okay? But let's see if Q1 was bigger than Q2, they will push out more of a field than Q2 could do. So you can have some electric field here. It won't be 0. It might be 0 here because this charge Q2 is weak compared to Q1. So the field might be 0 at this location, not in the middle. But if they will have the same magnitude, the electric field will be 0 in the middle.